Let's talk about diagonalization. Sometimes you have to erase a matrix to some power for certain applications, and that's not necessarily difficult. It's just it could take a very long time to do. However, if the power is not a whole number, like a to the 2.57, then it's not very obvious how to do it. So what can we do? Well, it turns out that if your matrix is diagonal, that it's actually very simple. Consider a diagonal matrix A0, 0B. Look at what happens when you try to square it. The result is also diagonal, and basically the entries are just A squared and B squared. And likewise, when you try to cube it, you get the same thing. It's like another diagonal matrix with now A cubed and B cubed. So you can see that in general, that's always the result. You get the diagonal entries being A to the n, 0, 0, and B to the n. Well, I mean, this is nice if you have a diagonal matrix, but what if the matrix is not diagonal? Then what? So the question is, can we make a matrix, like kind of force it to behave like a diagonal matrix? Check out this weird formula. A equals PDP inverse. Look at what happens. We're going to start by squaring it. So we write PDP inverse back to back. Now, look at the two middle matrices, right? P inverse times P. We know that those things cancel out. They just equal the identity matrix. So the P inverse times P, that's this I right here. Well, any matrix times the identity is just itself. So this D times I is D, or likewise, I times D is just D. So those two give you D squared. And so you can see that A squared equals P D squared P inverse. All right. That's interesting. Notice that the outer matrices were not affected at all. What happens if you try to cube it? So cubing it just means A squared times A. So we take our previous result times PD P inverse, and the same thing's going to happen, right? Because you have the P inverse and P right back to back. So they cancel out with the identity matrix. And so now you get D cubed. So yeah, if you're noticing a pattern, basically if you have any matrix that you can write with this formula, when you want to raise it to any power, it turns out like this. You get PD to the power that you want times P inverse. So that's kind of promising. And yeah, in fact, that weird formula is what we use to diagonalize a matrix when possible. It turns out that the matrix D is actually a diagonal matrix made up of eigenvalues, and matrix P is the matrix that is made up of the corresponding eigenvectors. And then P inverse, obviously, is just the inverse of P. Now, this is what the matrices look like. You see, the diagonal matrix has all the eigenvalues in the diagonal, and then for each eigenvalue, the corresponding eigenvector gets written as a column in matrix P. So does this always work? Well, it only works, obviously the matrix has to be square, n by n, and if for each eigenvalue the algebraic multiplicity is the same as the geometric multiplicity, then this formula works. Then the matrix is diagonalizable. So let's see an example of that. Let's say they give you this matrix and they ask you to find a suitable diagonalization. Okay. The first thing you want to do is find the eigenvalues and eigenvectors. And if you recall, we actually did this example in the previous lecture. We found the eigenvalues and eigenvectors. So the eigenvalues were 4 and 2, and the eigenvectors were 1, 1, and 1, 3. Okay, so once you have that, you want to write out matrix D and matrix P. Remember that matrix D is just the eigenvalues written on the diagonal. So here are eigenvalue 4, eigenvalue 2, and everything else is a 0. Now, could you have written it backwards? Yes, right? You could have put 2 and 4 the other way. So there's many options, right? Now, what's important is for matrix P, notice the vectors just became the columns, but the order matters. So if your first eigenvalue was 4, you have to use the corresponding eigenvector in the first column, right? And the second eigenvalue was 2. You have to use the corresponding eigenvector in the second column of P. So those have to match. So make sure that whatever order you choose, that they have to match. You have to stay consistent. And then you need P inverse. So remember that there's a nice formula for finding the inverse of a 2 by 2 matrix. And so the last thing you do is just put them all together. A equals P times D times P inverse. And that's the diagonalization of this matrix. And so like if you want to check if this works, you can throw this product into a matrix calculator and make sure that you get the original matrix right back. Now, another word about this is that, notice why did they ask find a suitable diagonalization, not like find the diagonalization? It's because there are an infinite number of possibilities. Not only because you get to choose the order that you write the eigenvalues, but remember that the eigenvectors, they were based on the value of the free variable that we chose. So, you know, like the first eigenvector could have been like 100, 100, or pi and pi. It doesn't matter. And so there is an infinite number of possibility of P matrices because it depends on what eigenvectors you chose. And therefore, there's always an infinite number of diagonalizations. Okay, so we said before that sometimes it doesn't work. And so sometimes you definitely want to make sure that it is diagonalizable. So this one is asking, find a suitable diagonalization if possible. So you want to start by finding the eigenvalues. And you remember the characteristic equation, the determinant of A minus lambda I equals 0. So you do that and you get the characteristic polynomial. And if you factor that, it's actually a perfect square. It's like lambda minus 3 squared, right? So you get that the eigenvalues are the same. They are a double root of this polynomial. So we say that the algebraic multiplicity is 2. Okay, we'll keep that in mind. Now we need to find the eigenvectors. So we start with the eigenvalue 3. And remember there was this equation A minus lambda I times the eigenvector equals 0. So, okay, we work it out, we row reduce, we got our row of zeros like we expect. And basically that first row is telling us that x1 is the negative of x2. So we could choose an eigenvector like this, negative 1, 1. Well, what's the problem? The problem is the geometric multiplicity is only 1, meaning for that eigenvalue, we only got one linearly independent eigenvector. So is this diagonalizable? Well, no, right? Because the algebraic multiplicity is not matching the geometric multiplicity. So like what that means is like if you try to make matrix P, you can't even make it square, right? Because like it would just be like negative 1, 1. It's literally a 2 by 1 matrix. You cannot make a 2 by 2 matrix. So this is an example of a matrix that you could call defective because it cannot be diagonalized.